Hello friends, in this video we will be doing some questions on Kirchoff's laws. I hope you have seen our previous videos in which we have explained the Kirchoff's laws and we have laid out some of the thumb rules which help us in solving some of the problems with KVL and KCL. In the previous video I have done one question and I have laid out the number of steps which we will be following again and again whenever we need to do KCL and KVL to solve some problems. I will not be going in the same depth as I did in the previous question, in the previous video, but I'll be mention those steps quickly and I'll be focusing more on the problem solving part and how this problem is different from that one. So this is the circuit diagram of a problem which we have in our hand. So we'll start with the same number of steps. Like first of all we'll name the corners. So let's say that A, B, C, D, E, F, G and H. So now we have named all the corners. Let us identify N, which is the non-overlapping loops. So here we can identify that we have three non-overlapping loops. So first one is this, second one is this, and third one is this. So the first one is A, B, F, G. Second one is B, C, D, H, and the third one is H, D, E, F. The third thing would be to identify the variables. So let us start with any of the branches and start naming the currents. So let's say I am starting from here. So this is X, X is going X. So B is the first junction we have encountered, and while naming the variables I have mentioned that we might need to use Kirchoff's current law. So at B the current will split and the outgoing current in one of the branches can be named as Y. In the second branch we can identify the current. So let us name the current outgoing from B as Z. Then the number of outgoing currents should be Z plus Y equal to X. So if this is Z, and this will give that Z equal to X minus Y. So I can replace Z by X minus Y so that I am not introducing any more variables unnecessarily. Now Y is moving from B to C and will keep on moving from C to D. So D is another junction which we have encountered, and now after point D the current will branch off again, and let us now name the current in D, E, F as Z again, and now we'll find out this Z. So because the terminology is same, so let us name it as Z dash. So the current moving here should be different than Z dash. So this current, so this is Z double dash. So Z double dash plus Z dash should be equal to Y. So this gives Z double dash equal to Y minus Z dash. So I can just remove this and I know that this should be Y minus Z dash. So this will be moving here. So the variables which I have introduced till now are X, Y and Z dash. So Z dash will continue moving here, will move up to this point, and now F is another junction, but and here we have X. So we know that the incoming current, so let us say this is some incoming current which is Z triple dash. So the two incoming currents Z dash plus Z triple dash should be equal to X. So this gives us Z triple dash equal to X minus Z dash. So we can remove just this. So we know that the current in HF branch would be X minus Z dash. And so while using KCL and while identifying the variables, we have not used the junction at H. So let us just check by doing the KCL at junction H whether the variables which we have identified are in correct order or not. So KCL at H. So the incoming current is X minus Y plus Y minus Z dash. This gives out X minus Z dash, and it is same as the outgoing current, which is X minus Z dash. It is always good to see at the last junction so that we can check that the variables which we have identified are correct or not. Because if we have done a mistake at any point in any sign convention or something, then it will be reflected and we'll get to know that okay, something is not right if these answers are not matching with each other. So we have done the first part, the second part, the third step. Now let's do the fourth step, which is applying KVL. And KVL, we mean that VAA equal to 0 around a closed loop. So let's apply KVL one by one in each of the loops. And so the first loop we have is A, B, F, G. Let's say we'll starting from B, B, B equal to 0 and in a clockwise direction. So this is the clockwise direction. So from B to F, first of all we are encountering the negative edge of the battery. So gain of 10. Then we encounter a resistor in the same direction as of the current. So that means a drop of IR. Then we reach up to H, and from H to F again we are in the same direction as of the current, and we encounter 4 ohms. So X minus Z dash. From G to F there is nothing. From G to A, now we are in the same direction as the current again, and we encounter 3 ohms. So it's 3x, and we hit the negative edge of the battery 6 volts. So it is a gain of 6 volts. So this will give us the first equation, which is minus 9x plus 2y plus 4z dash plus 16 equal to 0. So this is our first equation. Now for the second loop, which is BCDH, let's start from point C and in a clockwise direction. So C to D, nothing is there. From D to H, there is a drop of IR. From H to B, now we are going in the opposite direction of the current. So there will be a gain X minus Y, and we are hitting the positive end of the battery. That means a drop of minus 10. So this will give us a second equation, which is 2x minus 5y plus 3z dash minus 10 equal to 0. Now for the third loop, which is H, D, E, F. Let's say VEE equal to 0 and in a clockwise direction. So this direction, clockwise. From E to F, first we encounter the negative edge of the battery, so 5 volts, so a gain of 5. Then we are moving the same direction as the current, so 2z dash. Then from F to H we are moving into the current, so that is a direction opposite to the current, so that is a gain of X minus Z dash. And from H to D again we are moving in the direction opposite to the current, so it's 3 into Y minus Z dash equal to 0. So this gives us the third equation, which is 4x plus 3y minus 9z dash plus 5 equal to 0. So we have 3 variables x, y and z dash, and we have 3 equations which can be simultaneously solved to know the values of the variables. And similarly, what I explained in the previous question in the previous video, that after finding out all the variables, we can literally find out the potential differences, the current at each and every point of the circuit. So the circuit is completely solved. Only we need to do is that we need to apply KVL and KCL at different points to find out the different properties and different values at different points on the circuit. Let us do one more question which is a little different. So it seems different, but it checks other concepts and it's very informative in different aspects. So this is 60 volts. This is 10 ohm, this is 20 ohms, and this is 30 ohms. We are given that this is point A, this is point B, this is point C, and this is point D. And there is a current going in this branch as I1, and there is a current going in this branch as I2. We need to find out the values of I1 and I2. So let us follow the same number of steps and solve this equation using KCL and KVL. So the number of non-overlapping loops can we find out. First of all, we need to name whatever corners we are finding which are not named. Let's say this is B, so B is named. So this is E, F, G, H, I, J. So let's find out the number of non-overlapping loops. So the first loop is this one, second loop is this one, and the third loop is this one. So the first loop is E, so A, E, F, C. The second loop is B, D, H, G, and the third loop is A, B, G, H, D, I, J. So I'm just naming it so that it's clear to you that this portion, which is in this area, is our non-overlapping loop. So let us name the variables. So I can start from any branch, and from applying KCL and KVL in previous questions, we know that the variables is only introduced in KVL when it's multiplied by a resistor. So let's simplify the question and consider that branch AB has X current, branch BC has Y current, and branch CD has Z current. And the current incoming at junction A can be find out because we know that the current in this is I1. So I can find out that okay, in this portion the current will be X plus I1, but it will not be required because in the branch A, J, I, D we do not have any resistor, so we'll not be introducing this current value or this current variable because there is no voltage drop or no voltage gain which is associated with the resistor. So let's go to the fourth step and apply KVL. So in the first loop, let's start from point A and we'll continue doing clockwise. So from A to E nothing is there, from E to F to C nothing is there. From C to B there is a gain which is 20 into Y, and from B to A again there is a gain which is 10 into X. So which leaves us to this point at X equal to minus 2Y. So this is our first equation. The second is BDHG. So let's start from B in a clockwise sense. From B to C there is a drop of minus 20Y. From C to D there is a drop of minus 30Z. And then from D to B nothing is there because although the current value is there, but because we do not have any resistor, it does not contribute to any potential differences equal to 0. So this gives rise to Z equal to minus 2 by 3 of Y. So in the third one, let's start from A again in a clockwise sense. So A to B again minus 10x, Then from B to H we have nothing, from H to D we have nothing, from D to I nothing is there, from I to J because we are hitting the negative edge there is a gain of 60, and from A to J there is nothing. So it is very simple equation which gives us the value of X, which is 6 amperes, and using equation number 1 and 2 we can find out Y to be minus 3 ampere and Z to be 4 ampere. So what it says that the X, because it's a positive thing, it's moving from A to B, Z because it's 4, it's moving from C to D, but because Y comes out to be negative, it means that the direction of the current is different. So actually the current is flowing from C to B, but because we are considering the negative sign in the variable itself, so we do not need to specify the direction separately. Now apply Kirchoff's law, current law at junction A, or so we know that we need to find I1 and I2. So let us apply the junction law at B. So we know that the incoming current at B is X and is equal to the outgoing current of Y plus I2. So we are still following the same direction and the same variable notation because we can always put the negative sign to get the correct ones. So this gives us to the value of I2, which is X minus Y. So X is 6 minus of minus 3, which gives us 9 ampere. Similarly, if I am applying the KCL at junction C, so the incoming current is Y and the outgoing current, so incoming current is Y plus I1 and outgoing current is Z. So this gives us the value of I1 to be Z minus Y, which is Z minus Y, yes, 7 amperes. Oh, okay, so I did a mistake and Z was actually 2 by this formula, so 2 minus 3 of 2, so like I1 would be 2 minus of minus 3, so it will be 5 amperes. So whatever was asked in the question we are able to solve using KCL and KVL, but there is another thing which we can do in this question, and this question can be made simpler than what we used to solve this problem. So many of you must have identified that A, E, F and C is actually a zero resistance wire. So it's effectively a short circuiting concept which we have discussed in our previous videos, in which we discussed short circuiting and broken circuit. So because A, E, F and C are connected by a zero resistance wire, and one of the properties of zero resistance wire is that it may or may not have a current, but the potential difference or the potential at each point on the current is the same. So what we can effectively do is that we can use one of the properties of the zero resistance wire, that is its flexibility, that because there is no potential difference, I can either shrink it down or I can expand it. And similarly, we can also identify a second zero resistance wire which is there between B, G, H and D. So what we can do is that we'll try to shrink them down and see what the circuit looks like after that. So we know that point A and point C are connected by a zero resistance wire, so let's join them and write them as AC. Similarly, point B and D are connected by a zero resistance wire, so write them at the same point. Now fill out the other elements of the circuit around these points. So we know that A and B are connected by a 10 ohm resistor. B and C are connected by a 20 ohm resistor. So B and C a 20 ohm resistor, and C and D by a 30 ohm resistor. So 30 ohm resistor. This is AC and this is BD. And A and D are connected by a 60 volt battery. So it is clear to us by seeing this modified version of the circuit that 20, 10 and 30 ohms, all three are in parallel. So I can clearly define an equivalent resistance which will be a parallel combination of 10 ohms parallel to 20 ohms parallel to 30 ohms. And if you are finding out the equivalent resistance, you will find out that okay, 1 by 10 plus 1 by 20 plus 1 by 30, and this equivalent resistance will come out to be 60 by 11. The other thing is that because we can also, what we can do is that we can use the property of the parallel combination. We know that the same 60 volt is available to all these three resistances. So we can find out the different currents which are going in here. So we can find out X will be equal to the voltage across this resistor upon its resistance, which is 6 amperes, the Y, which is 60 upon 20 equal to 3 amperes, and similarly Z to 60 upon 30, 2 amperes. So you do not need to find out R equivalent as well. So you can clearly use the parallel combination property and you can find out the different currents which are flowing through 10, 20 and 30 ohm resistors. You can see that here we have assumed the direction of the Y from C to B, which is opposite to what we assumed earlier on. That's why we had directly got Y as a positive value. And after that we have like shrunk the circuit down and we have found out X, Y, Z. We can again expand it to its previous version and we can use the same KCL to find out the values of I1 and I2. So this is a really nice question because although it can be done by conventional methods of KCL and KVL, but there are always chances that you can apply the different properties which you know to simplify any circuit and then solve it. One good thing about KCL and KVL method that it's applicable in the complex circuits to simpler circuits as well. So while applying KCL and KVL, you need to practice a lot so that you are very handy in applying all the steps without listing them down, so that once a question comes, you will just write down okay, A, B, C, D, E, and you will start with the non-overlapping loops, naming the circuits and then solving them. So it will only come when you practice a lot. So we have covered 3 questions for Kirchoff's laws, but I would encourage you to do more questions from different books or from different materials, so that you will get a feel and handy of these formulas and these steps which we have followed in these examples. Thank you.